have Kelso from North Florida, and he's going to tell us about Halo simulation with the Baryons and the prospects for the detection of that. That's a welcome speaker.
All right, well, thank you for the invitation to come talk here. As Louis pointed out, maybe I should just tell everyone what an osprey is. So, an osprey is a seahawk. If you've ever heard the term seahawk before, it's actually an osprey. So, that's our mascot. UNF is located in Jacksonville. Probably you have not heard of UNF necessarily. And their basketball team is fairly good, though. They made the tournament last year. Hopefully they will again this year. We have a football stadium, but no football team.
Someone argued that's the inverse here.
Yeah. But they had a team before?
No, they've never had a team.
Oh, no, wait.
Oh, really?
That's right.
Yes.
What's the scale?
So the president of the university really wants to have a football
Sure.
team. So he had a huge football stadium built,
Yeah.
and so now the UNF soccer team plays there in like a 10,000 person stadium that has like 200 people that come to the game.
Really? Wow.
So he has aspirations to have a football team at some point, but it hasn't happened yet.
He collected money.
Yeah, football is big in Florida, not as big as in
Yeah, but still,
Texas.
it's a huge money.
It is, yeah. I don't know. This was before my time there. I arrived only a year ago, so I'm not sure. The stadium was definitely built by the time I arrived. Yeah, he's a really rich guy, so
Awesome.
he may have paid for it himself. I don't know.
Oh, there's nobody came.
Yeah. Okay, and so the work that I'm going to talk about here is stuff that I'm doing with Chris Savage, Monica Blurry, who's in Michigan, and Katie Freese, who's at Michigan also, Greg Stinson, who's at Max Planck, and Jeremy Balin, who I just learned today is at Alabama. I went and checked, and you all right? Yes, he's at Alabama. Okay, so I wasn't sure what the cross-section of the audience was going to be, so I have at least one slide in here to sort of give us a background on what the evidence for dark matter is, just in case it's not something that you think about every day. So one of our big pieces for evidence for dark matter is we look at the rotation curves. So when we plot the speed on the y-axis and the distance from the center of the galaxy on the x-axis, we sort of here are the observed points that we find when we look in galaxies. This is sort of what we predict based off of the amount of luminous matter. And so we have this big mismatch. So as we are extremely creative physicists, we just call this stuff dark matter. Right? Sometimes I wonder where we come up with our names. And another piece of evidence for this is through our gravitational lensing signals. So if you have sort of a large clump of dark matter or just general matter, and you have sort of a background galaxy, it can this can act as a lens and sort of give you different images of that background galaxy in between you and the Earth, and so that's kind of what we see here. So we see all these different little weird versions of some of these background galaxies that are coming from this lensing signal. And that lensing signal will give you an idea of how much matter is in between there, and we can sort of compare that with the visible light that we see, and again we fall short. So more stuff pointing towards this mysterious dark matter. The CMB is probably our biggest and most accurate measurement of the amount of dark matter that's around. So this is a fit with very few parameters, like 6 parameters, something like that. And the amount of dark matter that's in there is sort of governed by the match to these acoustic peaks in the cosmic microwave background. And going along with that, you need to sort of have Big Bang nucleosynthesis in there to give you how much baryonic matter we have. And so we know that the baryonic matter is sort of just a small fraction. So we have this CMB that tells us sort of what the total amount of matter is. Big Bang nucleosynthesis gives us the amount of baryonic matter, and so we know something has to make up that difference.
Does anybody worry about this very offline data point at the top of the CMB curve?
Which one? That one?
Yeah.
Yeah, I'm not sure.
Yeah, that's all.
Yeah, and there are definitely a few points that are sort of a little off, right? Here and
Yeah,
there.
there's the
Yeah.
power loss. But the
Yeah, it's not too, the bar is very small.
Yeah, but I guess when you do like a fit to the entire
Yeah,
thing,
fit
it
well,
still
fit
works
well.
very, very well. But yeah, that one point is a little bit
Don't worry about it.
Yes.
I think
If-
people have worried about, I forgot why or how, what the solutions, what the theory was.
the top.
Yeah, the top, what's going,
This
or
one?
why the loss, why the
For
deficit.
their reason?
There's various theoretical interpretations that I can't remember off the top of my head.
Or theory of spread?
Both, I think.
Both.
Both, yeah. I think there's still like cosmic variance issues.
Yeah, cosmic variance probably is the would be the real cause.
Yeah.
Yeah, and this is a pretty old plot, so I don't know, it may be
Yeah,
that.
with the Planck probably they changed.
Oh, that's a good point.
Yeah, yeah, so I don't know if this point is still as low, because this is, and this plot, I've been using this plot for like 5 or 6 years now. I guess maybe it's time to update it to a newer version. But. Yeah, and then some of what I'm going to talk about today is these simulations of large-scale structure and galaxy formation and so on. And when we run, or not when we, but when we in the colloquial sense run these simulations, we find that we need this dark matter around to give us this sort of cosmic web structure that we see. When we look out and observe the galaxies, it matches up pretty well to this picture that we get when we run these simulations, and if the dark matter isn't there, then those things don't match up. So all of this is sort of pointing us towards there has to be some extra matter around, and we're hoping at some point we'll be able to detect it through something other than just gravity, because basically everything we've talked about here so far has basically just been gravitational interactions. And so we sort of come to this sort of standard model of cosmology. The lambda CDM, the lambda is sort of the dark energy piece, and the CDM is the cold dark matter. And it sort of breaks down into, again, this is kind of an old figure, so the numbers are somewhat a little bit different, but the idea is the dark energy makes up the biggest part of what we see when we look at the universe on large scales, somewhere in the order of 70% of our energy. Dark matter is about 25%. Hydrogen and helium, only about 4%. Stars, neutrinos, heavy elements, just tiny fractions in there. And I always like to bring this up. So when I was at Chicago Rocky, Cole would always argue that this should be the distribution of the funding in sciences. So we should have 70% in dark energy, 25 for us dark matter. Sorry, neutrinos, chemistry, you get almost none. But unfortunately, it doesn't work out exactly that way. Okay, so I just make a brief mention of some of the ways that we're trying to search for this dark matter stuff. So in the end, as working on particle physics, we always have to sort of boil it down to trying to look at a scattering process where we have 2 dark matter particles and 2 standard model particles, and we're trying to figure out what goes inside this gray circle. And we have these sort of different ways to try to detect this interaction depending on which way you run the arrow of time. So this red arrow here is sort of representing the arrow of time. So if we run time this way, 2 dark matter particles can annihilate and produce standard model, and so that would be what we call indirect detection. So we're looking at trying to look at a place where there should be extra dark matter around, and if it happens to annihilate, then hopefully it can produce some extra standard model particles. Collider searches are sort of going the other direction, where we smash our 2 standard model particles together and hope that 2 dark matter particles might pop out the back side there. And then the direct detection, which is more along the lines of what I'll be talking about today, is where we have a standard model particle come in, dark matter particle come in, they interact with one another, and then we have dark matter and standard model coming out. And so there are various direct detection experiments, many more here that we could list, that are out there searching for these particular kinds of interaction. Okay, just to help you remember what goes into trying to measure a direct detection interaction, so what do these direct detection experiments look for? This is showing us basically the recoil spectrum that we would have at a detector, and it scales with the number of detector elements. As you can probably guess, the more detector stuff you have, the better. This row is representing the local density of dark matter where your detector is at, so here at the Earth, mass of the dark matter particle. And then we have to integrate over the velocity distribution, because it turns out that in this scattering process, any dark matter particle that has a sufficient sufficient energy can create this sort of interaction. And all the direct detection experiments that are out there now, at least the majority of them, only detect the energy. They don't detect direction or anything like that. So basically, anybody that's got high enough energy could deposit an interaction in your detector of that recoil energy. And so you have the integration over the velocity distribution of dark matter, and then the scattering cross-section. And so this minimum speed, basically, for a dark matter particle to deposit an energy in your detector is just dependent on basically the mass of the dark matter particle, the mass of your target nuclei, and what the recoil energy you're trying to measure is. And it's essentially just a kinematic expression here. And then the form that we'll typically use for the things that we're going to look at towards the end of the talk here is just the sort of standard spin-independent scattering cross-section, where we have sort of possibly different couplings to the protons and the neutrons. And then the form factor here sort of gives you how coherent the scatter is. So if the energy is big enough, then you eventually start to resolve the different constituent components of the nucleus. And so that's what this form factor is there. And the point of me sort of showing this is to help you remember that in a direct detection experiment, there is all kinds of physics that goes into it. So you need inputs from astrophysics, meaning we need to know what the local density is, we need to know what the velocity distribution of the dark matter is. The particle physics is in there in terms of what is the cross-section that we're looking at, what is the mass of the dark matter particle. And then even nuclear physics is in there, because we need to know if there is a recoil, how does that show up, and what are the nuclear physics aspects of this. So a direct detection experiment is actually more complicated than you would probably think at sort of just first glance. And we have to keep all of that in mind when it comes to thinking about what's going on inside these experiments. So in terms of this guy here, the velocity distribution of dark matter, the standard choice that's used by almost all direct detection experiments is what's called the standard halo model, or the simple halo model, sometimes it's referred to, often just labeled as the SHM. And it's basically a Maxwell-Boltzmann distribution. The way it cuts off at the tail is not always the same. Sometimes there's a hard cutoff like this. Sometimes people make it a little smoother cutoff. But the idea is you assume some isothermal spherical dark matter distribution, and you get, so this is basically a Maxwell-Boltzmann distribution as we see here, e to the minus something squared. And the dispersion velocity is basically the same as the rotation speed in the solar neighborhood. So it's how fast how fast the sun is basically orbiting around the center of the galaxy. And so what this means is it's inferred strictly from the mass distribution of the galaxy and not the actual particle velocities. So essentially the spread of the Maxwell-Boltzmann here comes purely from the distribution of mass. It's not actually coming from the summing up all the particle velocities. Okay? And as I said before, this is the model that's used by basically all of the direct detection experiments. So when you see results that they present, this is, I think in every single case I've ever seen, something akin to this is what's used. Like I said, they might have it cut off a little bit differently, but pretty much everybody uses a standard halo model. But you'll often hear people comment that this cannot be trusted as sort of what the true velocity distribution should be, because it doesn't account for the complicated gravitational collapse and merger history of our actual galaxies. And so, as alternatives, some people have looked at anisotropic velocity distributions, and others have found some alternative analytic fits that were thought to better match the true distribution, particularly at the high velocity tail. And so Louis has done a fair bit of work on this, and I think his figure is what I'm going to show on the next slide, looking at what some of these different functional forms might be. And these alternatives to the standard halo model are motivated, at least in part, by results of dark matter only n-body simulations. So to give you an idea of what those look like, this is sort of how we kind of envision the galaxies to form. You have these sort of clumps of dark matter that are all sort of orbiting some kind of a central mass here, and eventually they're sort of get absorbed into the bigger halo. But we sort of expect there to be a lot of sort of structure outside, big chunks kind of flying around. These would be sort of the dwarf galaxies. And so most of these simulations have been run assuming dark matter only, because dark matter is sort of a collisionless fluid. It's a much easier calculation to do than try to throw the baryonic physics in there. But in the last maybe 5 to 10 years, the baryonic physics has started to be thrown in there as we've got more and more computing power and better at trying to describe the baryonic physics. Things have started to sort of ramp up in that respect. But this is a graph. I'm pretty sure this was from your paper, right, Louis?
Yeah, it was led by a graduate student at Stanford.
Yeah. So Louis and some of his collaborators worked on this. And so this is basically the velocity distribution that we've been talking about, plotted as a function of speed, basically. And so what this is showing you in gray is some of these n-body simulations. And then these curves are sort of different analytic fits to the n-body data. And so, for example, the thing that is in blue, that's what was the standard halo model. And so if you look at this curve in particular, it basically tracks the, what is this color? Cyan?
I think
Cyan?
Yeah.
What is it?
Cyan.
Cyan? Yeah. This light turquoise color or whatever. So this is showing you the n-body results are the histogram, and you can sort of see that the standard halo model doesn't do such a great job of describing the n-body results. In particular, it decays much too quickly in the tail, and the peak seems to be shifted off a bit, and it peaks a little bit too high. And there are these other sort of analytic forms that people have put forth that do a better job of describing the sort of n-body results of galaxy formation.
But those don't include baryons, right?
None of these included baryons, right? Yeah, if you have any questions at any point, feel free to
Well,
just...
there's a simulation result in the Sine color. So how much variance does that have?
Sorry, I didn't catch the first part of what you said.
So for this body simulation result, is this a good one, or there might be some a lot of variation depending on what kind of initial state or some different assumptions you're making in the simulations?
Yeah, so at this point, nobody has done a really great job of describing how galaxies work, how galaxies form yet. I think that's a pretty safe statement to say.
So I was just curious, if you run another simulation, maybe with another set of assumptions.
I think in general the n-body results are all fairly similar. I think this one is Rhapsody, right?
Yeah, actually, to that the gray histogram comes from stacking many different halos together in a single simulation. So it's not just like one halo in one simulation. It's like the cumulative distribution of hundreds of halos in a given simulation.
What are the black curves?
So the different curves are just different sort of fits. Partially this is to show you that there's lots of different ways that people might postulate to try to describe the velocity distribution of dark matter. And I think, Louis, which one do you remember?
I think the black curve is the end. So the student Yao
is that the one that you all
who led this project? I think the black one actually is the best fitting.
So what's the physics of this falling down?
What's the physics of the falling down? You
Compared to the green. Green does continue. This is because just fitting, or is because some physics?
I mean, Well, I guess the physics is you're losing particles at high velocity for some reason.
Green doesn't have.
It's still there, it's just, these are all just different functional forms.
Right.
And none of these, I would say that almost all of these are just phenomenological. I think you're just saying, I'm going to fit a function that looks similar to this. And
So, but this question is more like what's the data which is given you? Like, is it like one n-body comparing with another n-body, or is there any data you were using?
no, so these are just n-body comparisons. Yeah,
So
yeah.
there is no data.
So it must be physics.
Yeah, yeah, some n-body.
And why the lab simulation devices?
Yeah, that's a good question. I don't know what goes on.
That's just a
with that.
peculiar function that we're using to fit that.
Oh, okay.
It's just, you know, a polynomial or something that, you know,
Okay.
that's yeah, exactly.
Yeah. Any other questions? And so, in addition to the fact that it seems like the standard halo doesn't do such a great job of describing the velocity distribution of dark matter, there are other small-scale problems with cold dark matter. Louis, actually, I think this was what your whole talk setup was about, right?
Probably, yeah.
Yeah. So hopefully I hit most of the points that you did and I don't screw it up too much. So bulgeless disk galaxies is something that basically has been identified as something that cold dark matter has a bit of trouble explaining. So basically when we look, sorry, I went too fast. When we look at galaxies in general, the bulges all tend to be smaller than what the cold dark matter simulations predict. So when we observe them, in general, they tend to be smaller, and there are even like disk galaxies that don't seem to have bulges. And the cold dark matter simulations don't tend to produce this. And so this is sort of a problem with some of these n-body simulations. The core cusp issue is something that's been around for quite a while, and what this is sort of showing you is basically the data points are when you observe galaxies, and sort of what the dark matter only simulations are sort of showing you, predicting that the density of dark matter should rise fairly steeply as you go in towards the center of the galaxies. But when you actually go and look at these galaxies using surveys, you find that instead it doesn't rise nearly as much as these cold dark matter simulations predict, and in fact it kind of more levels off, something like this. And so the cold dark matter simulations predict a more cuspy profile where it should, you know, rise fairly steeply, but when we actually go and observe, it's sort of more of a chord profile here. And so trying to understand, you know, what's going on with the cold dark matter simulation, why are we not getting this shape? This is another sort of problem that has been identified with some of these n-body simulations. And again, you're just sort of extrapolating. So these n-body simulations can't go to super small numbers of particles, and so these are all sort of extrapolations to the size scales that we're talking about here. This is another one that's talked about a lot, the too big to fail galaxies. So basically, n-body simulations tend to predict, so I should have that. We'll go way back to that picture in here. So we notice that there are, you know, these sort of satellite galaxies that should sort of be around your kind of central galaxy. And it turns out that most n-body simulations predict that there should be more large satellite galaxies that should have been able to form stars, that we should be able to see, basically. And so that's where this too big to fail term comes from. There should be a lot of galaxies that or a lot of dwarf galaxies that are too big to fail to have formed stars. So we should, you know, see these large things, and when we look in particular with the Milky Way, we don't find these sort of things, or at least not sufficient number. And that leads into sort of the missing satellites problem is another one that is maybe not as big of a problem in some people's mind. So the idea is we have sort of the known satellite galaxies that we've found so far, and then there's a few more that are now starting to crop up now that DES has been running. So we've seen, what is it? I think there's like 8 prospective galaxies, something like this, right?
2015-ish.
15, okay. So in the past, people were sort of worried. It seemed like there should be more of these things around because we only knew about 10 or 15 of them, and it's already bumped up to, I guess we're now getting the order of 50 or something like that. And so it turns out that all of these things can sort of be addressed by including baryons in the simulations. So there are various people who sort of argue one way or the other, but it tends to be if you ask somebody who does these baryon simulations where now we put baryonic physics into the formations of galaxies, they would say that they can basically explain all of these things. And so an example of this is now with that missing satellites example that I was discussing before. The original, when we had sort of the cold dark matter only simulation, this is showing you basically the number of satellite galaxies as a function of the circular speed. You can see that there's a whole bunch of dashed curves here, and then once you throw the baryonic physics in, you remove a bunch of these galaxies at the higher tail and push them towards lower circular speeds. And so you can sort of explain all of these things in one form or another using baryonic physics. And whether or not that can take care of all these problems is still a point of discussion, and I don't know that we will know the answer to that for some time until somebody has like 100% verifiable, yeah, this is a good description of galaxy formation. In particular, there has been sort of an explosion of a bunch of different simulations that are out there that are trying to include the baryonic physics in galaxy formation. And the one that we're using is called the MaGICC simulation. So as physicists, we seem quite good at coming up with acronyms, even though we're not as clever with naming things real names. Like dark matter is sort of a lame description, but we always have like MaGICC and these other cool names that we come up with for our acronyms.
But the worst one, because matter is consists of matter and antimatter.
Yeah, it's true. And so these simulations in particular are, it stands for making galaxies in a cosmological context. And so there are various different versions of this that you can go take a look at. There are videos showing you, and these are sort of the different, looking at the simulation in different forms, like this is the temperature, this is the, I can't even read it very well, sorry, the metals, the stars, so there's all kinds of various things. And each of these different G's basically correspond to different particular halos. So the idea is it was a cosmological size simulation, and then what they did is they sort of zoomed in on a few particular halos and did some really high resolution analysis of those guys. So these are sort of some of the halos that they picked out, and then did much higher resolution simulations to try to get at what the galaxy formation would be in these particular halos.
Just out of curiosity, could you just very simply tell me what does it mean by the close and far? And
oh, these are just videos. So if you downloaded them,
I see.
and so the close is you're like zoomed in on the video, the far is you're further out. Yeah. So it's just. I think the Cosmo is the dark matter only piece, and then there's the metals, there's stars, there's gas, all kinds of different videos. So it just sort of focuses in so you can see what's going on with those different components of the simulation. Okay, and so these MaGICC simulations use the results of this MUGS, and so this slide is here for anybody who's sort of an expert in this area, which is not me. So I will do my best to sort of put this up there so that way if you know what all these things mean, then that's good, and if you don't, you can sort of zone out as we go through this. But it's a set of high-resolution galaxy formation simulations of L-star galaxies performed using, so it's smooth particle hydrodynamics, so the hydrodynamics is in there, and it's an n-body code called gasoline, which I think is a pretty common code to use. I had at least heard of that before starting to work on this project. As you can guess, this is not my area of expertise. My area of expertise is more the direct detection side of things, so I'm doing my best to present this in a way that makes sense, so hopefully it does by the end. They include a treatment of low temperature metal cooling, UV background radiation, star formation, stellar feedback. So all of these things are things that weren't there when you're talking about the cold dark matter only simulations. Okay? And so again, you don't have the particle resolution to like zoom down to the size of a single star or things like that. So you're always using some prescription to try to describe the actual baryonic physics that's going on. And so that's what these things are talking about. So you sort of try to describe star formation, stellar feedback, supernova, and there are different ways, different prescriptions people use to try to describe that baryonic physics in there. And from what I can tell, most people agree that the way that these guys are doing it is a pretty good way. And so, as I said, this was a cosmological size scale simulation that they then grabbed particular halos that they zoomed in on and sort of re-simulated at very high resolution. And they chose that randomly from halos of mass about 0.5 times 10 to the 10, or 5 10 to the 11th up to 2 10 to the 12th. So sort of in the Milky Way's mass range, because the Milky Way is somewhere around 1 10 to the 12, something in that range. Without regards to the merger history, spin parameter. So the idea is they're trying to do they're trying to be as unbiased as they can. So this lack of selection bias lets you sort of compare not only the mean properties of the galaxies, but also the distribution. So just to give you an idea of how general your conclusions might be. Okay? So the particular ones that we looked at is we wanted to sort of grab a few that were relatively similar to the Milky Way. And so we took, our results focus in on 3 different particular halos. We have G1536, which is dark matter plus baryons. The virial mass is a little bit below the mass of the Milky Way. And the circular velocity is a little bit less than what we would expect. So for the Milky Way, we think that this circular velocity is somewhere around 220 kilometers per second. So that tells you that the Milky Way is probably somewhere in between these 2 galaxies here. This one's a little bit heavier, this one's a little bit lighter. And then we also, for comparison, use this simulation, G1536, which is basically identical to G1536 here, but with dark matter only. So basically rerun the high-resolution simulation, but remove all the baryonic physics and just allow the dark matter only simulation to be there. So this way we can get sort of a direct comparison with all the same initial conditions and so on as to what the difference between adding the baryons is compared to the dark matter only simulation.
Chris, I have a question. So people also did warm dark matter.
Yes.
Do you know what did they get for the galaxy simulations? Do they fit all this virial mass and all this stuff correctly?
Yeah, so warm dark matter can do very similar things to including the baryons. So if you talk to who is it? Who is it? Frank?
Carlos Frank.
Carlos Frank? Yeah. He's somebody who does a lot of these simulations with warm dark matter. And if you have warm dark matter at around, what is it, about the 5 to 6 keV range, something like that?
That's all right.
Yeah,
Actually, she's an expert. She's done similar simulations.
So, but then I have a question. So, if I use baryon on top of warm dark matter, would those warm dark matter models be ruled out? Just I want to see the freedom of baryons.
That's a good question.
They do predict weird baryon something. So yeah, they have difficulty to calculate that. So, but there are some conversion inputs, but they do predict some weird.
Yeah, but suppose I add baryons on top of warm dark.
Yeah, that's you got that.
Okay, and then do you get good fit?
They still need to cover that, but they do get some good stuff.
Actually, I think the way to think about it, maybe there's a lot of knobs you can tune.
Yeah.
If you change all the dials in such a way, you can get something that works.
Still, no. Because
that-
some of these things are drastic, right? There's like a varial radius, varial mass, and then the circular velocity.
Right.
Which is like a 187 to 73 versus 108. So it's quite a bit of difference. So I was wondering if you add one dark matter on top of baryons, probably you will go beyond what you observe or what you expect. So can we rule out one dark matter by having baryon in your band? So that's the thing I was.
It's an interesting question. I'm not sure.
So remember too, these are for like one specific halo.
Yes.
In one specific halo in a simulation. So there's probably, if you looked at a whole sample of these, there'd be a scatter. And
Yeah, there's definitely going to be scatter in there for sure.
properties, yeah.
What is the U, V, W?
So U, V, and W are your galactic coordinates. So U is like
Okay.
radially towards the
Okay.
galaxy center. V is in the direction of the rotation, and W is up and down. I was going to get to that on the next slide, I think. But yeah, maybe I should put that in sooner. This table is just to sort of give you an idea that we're picking, we picked particular galaxies that were pretty close to the Milky Way, just because that's kind of what we want to compare to. And then we sort of used 3 different functions to fit the velocity distribution of the dark matter in there. We have the standard halo model, which again, is not actually using the particle velocities. It's just the the Maxwell-Boltzmann distribution width is just given by the rotational speed. And so that's basically these guys here. And on top of that, you sort of have to give the escape velocity because the Maxwell-Boltzmann tail doesn't go out to infinity because a certain set of particles can escape. And we just sort of grab the highest velocity particle that was still around in the simulation. That's where we're pulling this V escape from. On top of that, we also did a best fit Maxwell-Boltzmann, which means we don't enforce V0 to be V rotation. We actually allow that to float. And so we basically do a fit to the particle velocities. So this is not something you could actually really do because we don't know what the velocity distribution of dark matter particles are in the galaxy. Right? We can't actually measure this. But you could envision using this as sort of one of your fit parameters, just saying let's allow that V0 to vary a bit. And on top of that, we allowed a best fit Maxwell-Boltzmann, but also allowed some amount of rotation. So in addition to giving the freedom to let V0 go to a different value, we also allowed some rotation of the dark matter halo as well. And that's sort of, if you've heard of the term dark disk, there are some people that sort of propose that there may be a dark disk that's sort of co-rotating with the stellar component. And so we sort of include that in there, and we find that in general, if there is any rotation, it's pretty small, at least in the galaxies that we looked at.
Escape speed has to be micromanagement, like only Q number change.
Only which numbers change?
Escape speed.
Mm-hmm.
It looks like 600 or 602. It's a tiny change. Do you have to do this kind of micro correction or?
So you
It's kind of integrity over something, right?
right. It's just some number that you have to throw in there
Yeah.
because we know that at some point the velocity is going to
Right, but
tail off.
Yeah.
But the number that we use here is not very important. No.
Okay.
And the only case where it might be sort of important if you're talking about particularly light dark matter, like somewhere less than 10 GeV or something like that, because those particles are so light that they don't have very much energy, and so then the tail can become important there. But anything above about 10 GeV, the V escape is going to be almost unimportant. Okay. And so this is some of the results of what we found. So we'll kind of go through various different parts of this. So here's the velocity component in the direction towards the galactic center. So that's what U represents. And here again are the 3 different simulations dark matter only, 1536 that includes the baryons, and then 1784, which is the slightly heavier one. There are various curves that are shown on here. The n-body results are what are shown in black, and that's usually pretty obvious because it's sort of this scattery looking thing. The inferred standard halo model is the sort of what's shown in green here. And then the Maxwell-Boltzmann fit, where we allow that width of the bolts of the Gaussian to vary, is what's shown in blue. And then the rotating Maxwell-Boltzmann is what's shown in red. And the error, or sorry, the width of this is supposed to basically give us an idea of the scatter in the results based purely off of particle number. So essentially what we did is we just took the underlying curve as the distribution of the dark matter, and sort of did like a bunch of extra simulations, essentially like 1,000 simulations, and this gives you the scatter of what that would look like, assuming your parent distribution was the dark curve that's shown in there. So this is just an idea of how wide of error bars would be there, just purely based off of particle number. Okay? And so we see that in general for the dark matter only simulation, yeah, definitely the standard halo model does a pretty poor job of describing the velocity distribution. So it peaks way too high, and it's got, what's shown down here is the relative difference. Sorry, I forgot to point that out. And it's the relative difference compared to the rotating Maxwell-Boltzmann. If you compared everything relative to the n-body results, the curves just look really crazy and it's hard to interpret. So everything is just taken relative to sort of the best fit curve of the Maxwell-Boltzmann guy. And so we can see that the n-body results don't fit very well with the standard halo model, but when you include baryonic physics, you know, it's doing a pretty reasonable job. There are definitely still discrepancies in this velocity component, the one towards the center, but the standard halo does a much better job of describing this, pretty much as good as these other two functions that we fit with once you include the baryonic physics.
Sorry.
Oh, yep, go ahead.
In the middle center plus, the green is just behind the red?
Yeah, the green is, so if you, in this first one, the blue and red overlap. Here, all three pretty much overlap. And then on this one, they again pretty much all three overlap. The green squeezes a little bit out. Yeah. So they're all there, it's just sometimes one of them is hidden behind the other one. This one is for the component of velocity that is in the direction of the rotation. And so again, we find that the standard halo does a pretty poor job of describing the velocity distribution. In the dark matter only simulation, adding in the baryonic physics though definitely makes it a better fit. Here in this one, the green is actually behind the blue because they almost lie on top of each other for this whole simulation. And then we again see that including the baryonic physics in these two guys, the velocity distribution is much better fit than it was over here for the standard halo. And the final one is the velocity into and out of the galactic plane. And so this one is actually one where it probably does the best job of describing the velocity distribution once you include the baryonic physics. And again, there's much larger spread here, so it seems like the standard halo isn't doing all that terrible of a job, even in the dark matter only simulation, but it matches quite well when you include the baryonic physics. What we need to do to, if you remember, to calculate the velocity distribution, though, we need sort of to integrate over the speed distribution. So this is what the speed distribution would look like in the galactic frame. So this is essentially caring only about the magnitude now, so combining all those guys together to give you the magnitude. And so this is the case that people basically refer to when they say that the standard halo does a bad job of describing the velocity distribution of dark matter in the galaxy. So you can see the green curve here, when you have a dark matter only simulation, it does a pretty poor job of describing the n-body results. So in this case, it peaks too early, it's much too high, and the tail decays much too fast. But we found that when we included the baryonic physics here in the same simulation as this one, and then also in the heavier version, that as far as the speed distribution in the galactic rest frame goes, it actually does a fairly good job of describing the n-body results. There are deviations here and there, but nothing too drastic, even close to what you find when you compare to the dark matter only simulation. Now, it turns out that we are on Earth, and so we can't just take the galactic frame. We have to account for the motion of the sun plus the motion of the Earth. So you have to sort of take that velocity distribution and boost it into the frame of the Earth, and that's what I'm showing you here. And so we can see that just taking the velocity distribution in the galactic frame and boosting it into the Earth's frame, it actually sort of gives you a better fit for the dark matter only simulation. Still, it's not very good, and it has the same problems that we pointed out in the last one, but it's even a little bit better fit than before. And we again find that for the baryonic physics included simulations, we find that the standard halo does a pretty good job of describing the n-body results here.
So compared to this slide, to the previous one,
Yep.
in the plot in the right-hand side, there are particular structure for in-body simulation.
There's what?
In-body simulation, the bump structure, which disappear for after Earth frame. What's going on?
So, like this structure here?
Yes, that's there, yes.
Yeah. So you can see it's sort of a little bit there, but yeah, it's definitely not there as well. The only difference between these two is basically boosting into, so it's adding in the velocity adding in the velocity of the Earth. And so I guess it must be that the way that these particles are sort of showing up, it must get smoothed out when you include the motion of the Earth. Okay. And if you recall, in the end, the thing that we really need is the integral over the velocity distribution. And so that's sort of what I'm plotting for you here. This eta represents this integration over the velocity distribution. And we see, again, for the dark matter only simulation, it does a pretty poor job, especially at the tail. And this is really the thing that people sort of point to the fact that the standard halo model is not good, especially in the tail. And we find the same results that everyone else is finding. When you are doing a dark matter only simulation, that yes, at the tail, the standard halo model does a very poor job, at least for this particular one we looked at. But when you include the baryonic physics, it definitely does a better job, so it's staying closer longer. We see that it still is not doing a great job of describing it out at the tail, but it's significantly improved to what it was before. And it's even a little bit still kind of not so great out here at the tail. And at this point, it's not really clear whether or not this is coming from particle number, like is it just that there aren't a lot of particles out there, because this is getting to be pretty high velocities out here. And so really, at this point, we're not really sure whether the standard halo model is just now starting to not be so good, or if there just aren't enough particles out there to really give a good description of what the velocity distribution actually looks like out there. Okay. And so just to remind you, so this was our velocity, our recoil spectrum that we expect inside a direct detection experiment. And because of the motion of the Earth, we actually expect an annual modulation to this signal. So in general, the sun is orbiting the center of the galaxy. And so then in the sun's rest frame, there's basically a wind that's sort of flying into the sun. As I said, somewhere around 220 kilometers per second. This is sort of the bulk motion of the sun. But on top of that bulk motion, the Earth is orbiting the Sun. And so what that amounts to is that in June, there's a component of the velocity of the Earth's rotation that tends to point the most anti-parallel to the sort of bulk motion of the WIMP wind. Whereas in December, it points the most parallel. And so that means in this time of year, we can access higher energy collisions than we can in this time because the center of mass energy is higher there. And so you sort of expect this annual modulation signal. And so then what we do based off of that is we do an expansion for the velocity distribution in terms of a Fourier series. So you have sort of the average component, and this is what most dark matter experiments are looking for, and then a cosine component and a sine component. So in general, if everything is spherically symmetric, then we would expect everything with the way we've defined our Fourier series to be purely cosines. And so this shows you what the modulation amplitude looks like as a function of the speed of the dark matter particles in the simulation. So again, the black is the simulation. And we see that, again, for the dark matter only simulation, the standard halo model doesn't do such a great job. But once you include the baryonic physics, the standard halo model actually does a pretty darn good job of describing what this modulation amplitude would look like. The first order sine component is something that we're still sort of trying to understand a little bit, being that if everything was isotropic, if we had these isotropic dark matter distributions, this component should basically be 0. And that's what we find, you know, when you look at the different fits to this stuff, all these fits are predicting 0 because we're assuming that everything is isotropic. But when you actually look at the n-body results, we find that, especially in the dark matter only simulation, but even in this one that includes baryonic physics, the sine component is not actually 0. So there's actually some sort of non-negligible components here. So if you look at this, it's up to about, I don't know, 2/3 of 10 to the minus 4. And so that's somewhere around right here. So, you know, it's a non-negligible fraction there. And so we're still trying to understand what is the reason why we're getting some non-negligible sine components here. And we think it has something to do with the fact that we're assuming everything's isotropic and maybe it really isn't. So then the $1 million question, if you don't know this reference, you should go watch Austin Powers. So how would direct detection experimental results be affected by the differences among these various halo models? So that's in the end what we're trying to get at. You know, we have shown that, at least with these results, it seems like adding the baryonic physics does a better job of describing the dark matter velocity distribution. But in the end, how we're going to get at this is using a direct detection experiment. So we need to know what will this do to our direct detection results. And so we sort of picked 3 different experiments to compare with. So we have the DAMA results, and we're using those as basically a confirmed signal for an annual modulation signal. Whether or not that's true is still up for debate. No, you know, everybody knows DAMA is measuring something, 9.3 sigma measurement of an annual modulation. Not everyone is confident that this is a dark matter signal. It is consistent with that, though. So then what we're doing is we're just going to say, if there is a dark matter annual modulation signal, it's going to look something similar to what DAMA sees. So we'll just take at face value that DAMA is measuring dark matter and apply this to our n-body results. In addition, we also looked at the CoGENT results. So these this is a germanium detector. If you didn't remember, DAMA is a sodium iodide detector searching only for the annual modulation signal. The CoGENT detector is a germanium detector, and it's much smaller. So DAMA is 250 kilograms. CoGENT is 0.33 kilograms, so it's much smaller. And they found some excess of results, or sorry, some excess of events at low energy in their first run. They released some data, and so initially there was a lot of excitement because people thought that this might actually be sort of a confirmation of the signal that DAMA sees. Since then, pretty much everyone has agreed, including the collaboration themselves, that this is actually probably a background, most likely surface events. But we're sort of using their spectrum because it's completely consistent with the dark matter interpretation as a sort of postulated germanium signal in a germanium detector. We'll skip over that. And then Lux is currently the detector that has the strongest limit for direct detection. Pretty much all masses. It's 370 kilograms of liquid xenon. It's a sort of time projection chamber, and it measures both the scintillation light and the ionization signal. It's about a mile underground in South Dakota. So if you ever go to setup, you'll get to, or at least for one more year, you'll get to go check out what's going on in South Dakota up there. Just so you know, I was born in South Dakota. So I may be the only person you've ever met who's born in South Dakota. Yeah, but you go to South Dakota. So let me clarify that statement. Outside of South Dakota. So if you're outside of South Dakota, I may be the only person that you've ever met.
Beverly. I don't know.
No, she is from Wyoming.
No. I was
Very,
thinking
also
probably-
very unlikely. Even more unlikely than South Dakota. And so this is kind of the picture of what the direct detection looks like in terms of present and future stuff. So anything that's showed as a dashed curve here are sort of predicted or anticipated results. Anything that's a solid curve here is a already measured sort of exclusion curve. And anything that's closed is sort of some postulated signal. So the ones that I was talking about before, DAMA here, CoGENT is in there, and then the Lux limit, I think this thing preceded the Lux limit, so the Lux limit isn't shown on here. Oh, no, it is there, sorry. There it is, the green one right there. Okay? And this just kind of gives you an idea of where the field is at now, where it's going to go. And this is, finally we've come to the crux of it, what I'm showing on here. Again, these are the 3 simulations. The top 2 are including the baryons. The bottom 2 are dark matter only, and I'll discuss exactly what these 2 are. What's shown as the dashed curve is what you would get in the mass cross-section plane for the best fit for the n-body results. So you take the n-body results and you isolate out where is the best fit. And so that's what the purple is showing, the DAMA regions. And so these are based off of just the annual modulation signal. This is primarily scattering from sodium. This one's primarily scattering from iodine. Okay, I'm sorry, I said that wrong. The one that's shown in the solid curve is the n-body results. The one that's shown in the dashed curve is the standard halo. So you can see that for G1536, there's virtually no difference between the n-body results and the standard halo model. If you look at this particular galaxy, just G1536. If you come to G15784, again, you find something fairly similar, that the results are pretty close. We do get a bit of a shift here, in particular for the iodine region for DAMA, but in general, it's nothing too bad. The largest discrepancy that shows up on Lux is at the low mass region, and that sort of comes from the fact that, again, for the low mass region, you're looking at stuff at the tail of the distribution. And so we would expect, if there are differences, that's probably where the differences are going to crop up. And in particular, that's what we definitely find when you look at the dark matter only simulation. So again, remember the solid curve here is showing the n-body results, so that's the same in these figures. Basically, it looks pretty close to the same. The dashed curve is what you get for the standard halo. And one thing that's sort of interesting is, for example, the low mass region for DAMA completely disappeared if you were to use this galaxy and take the standard halo model. So that sort of shows you that in the dark matter only simulations, that yes, we tend to agree that you don't do a very good job, and it even could give you a region that disappears when it should be there when you're talking about when you're talking about using the standard halo to try to describe the physics of what's going on for a dark matter only simulation. And again, we see that the xenon, or the lux bound here, sorry, fits the worst down at low masses because that's where you're sampling basically just the tail. But once you hit the broader distribution, that even in the dark matter only simulation, you do a pretty good job of describing the limit. So that's sort of pointing out, if you're only finding limits, it doesn't really matter which velocity distribution you use. It's probably going to give you about the same result. If you're trying to do fits, then to a proposed signal, then maybe it would matter a bit. But if you sort of include the baryons in there, then it seems like the standard halo actually still does a pretty good job. And this over here is also another dark matter only simulation, but this now, the dashed curve on this one is representing where we've allowed the V0 and the rotation, so it's the best fit rotating Maxwell-Boltzmann to show that if you throw in a couple of extra parameters that you allow to be fit as well, that you can still do a pretty reasonable job of reproducing the actual n-body results. So if you throw more parameters in, you're going to be able to still fit the physics pretty well.
So how does this dark matter mass difference with another simulation?
So this dark matter mass has really nothing to, sorry, maybe I should get a clarification. What do you mean by the dark matter mass and the n-body
those
simulation?
contours on this cross-section versus mass plane.
Right.
Which means by choosing this area, you're saying this inside this area, they are doing better in other simulations.
Yes, so the yellow, or sorry, the orange curve here and the purple curve here are the 3 sigma contour regions that fit. This is the CoGENT signal, this is the 2 DAMA signal.
Oh, okay.
So we're using the actual signals from those experiments. And so then if those experiments happen to exist in G1536, these are the values that you would measure there. Do you understand what I'm saying? So we took the data from the experiments, and so only a certain mass and cross-section range will fit that data. And this is what the data is that will fit it. So for G1536, the colored in curves are using the n-body results. The dashed curves are if we use the standard halo model.
Oh, I see. Okay.
And so it does, the standard halo describes almost the same physics as the n-body simulation is what I'm saying in this guy here, this guy here. But in the dark matter only simulation, we can see there's actually a fairly large difference between the two.
Using a different velocity distribution.
Yeah. Yeah. 2 different velocity distributions to fit the same data. Okay?
That's a little bit of surprise, right? Why is there with the lower plot, the standard halo model does not fit?
No, that's what we expect, right? So if you go back to, if you go way back to the beginning. I'm almost done. We see, for example, in these n-body simulations, the standard halo is in blue, it decays way too quick, right? So we actually expect this. This is the behavior that we would expect. We would expect that the limit should become weaker. The limit should become weaker at low masses, which it does, because you expect fewer scatters there, according to the standard halo. All right? And so we finally come to our conclusions. The conclusions are maybe the standard halo model ain't so bad, because it seems like once you start to include baryonic physics, that maybe it's actually going to do a reasonable job still of describing what's going on. And if you don't know who this is, you just must not be alive. Huh?
Or you weren't born in the 80s, you were born after the 80s.
Even if you were born after the 80s, come on. Everybody knows Michael Jackson.
Okay.
Any questions?
All right, thanks.
Any other questions?
So, I've been, so this result you see with the baryons making a more standard halo model like.
Mm-hmm.
This is something that, as you mentioned, been seen in other simulations too.
Right.
And I actually don't know, I don't have a feeling yet for whether this is just luck, some combination of luck, or that there's actually real physics here.
Right.
In terms of how the distribution is getting set. Say the dark matter particles are interacting more randomly in some way with, baryons as they do their thing, and sort of this randomization process gives you more of a Maxwell-Boltzmann type distribution. Because I think the interpretation of the dark matter only simulations is that it's not a pure Maxwell-Boltzmann distribution because you don't have sort of these random particle interactions that are happening. Actually, the funny thing is too is if you look at self-interacting dark matter simulations, people have done this exercise here with self-interacting dark matter, where the dark matter interacts and scatters. That actually looks more like a Maxwell-Boltzmann distribution standard halo model. So it'll be interesting here to see as the baryonic simulations keep getting better and better whether this converges on the truth and there's actually real physics behind this. I mean, right now there may be, I just don't know yet, but this would actually be pretty cool if there was. Actually, I guess I don't have a question there, but my question was, have you looked at the shapes of these halos? Are they more, because the dark matter only ones tend to be very elongated.
Yeah.
And I think the one when they add baryons, they typically tend to be more rounded. And I think there's ways that this is explained.
Yeah. So this is what they look like.
Okay.
The figure's kind of small to see. Sorry. This is something that I didn't include in the plot because we're in the talk because we're still working on these. But here are the three different simulations. Here's the dark matter only. Here's the 1536 and then 15784. And so there's this, and then I'm not sure which particular thing you would want to see, but when you look at maybe the other.
Just like in real space, like the shape, just the axes ratios. Like
yeah, sorry.
In cold dark matter, they're triaxial halos,
yes,
right?
let me pull up this.
Yeah, but
let me pull up this.
I guess it's just say cold dark matter only.
I have another plot that will show you exactly what you want to see. I think. So that is.
So you are trying to look at the velocity distribution.
Well, actually, but I'm just wondering. Yeah. So right. So for Heath's case, yeah, this is I guess a separate question. How do the baryons affect the halo in general, and do they affect it in the same way? Yeah, but so the question I asked is independent of velocity, right?
But the low velocity, I think that's the place that's the place where the physics is.
Low velocity.
Low velocity, and that's the standard halo model probably makes you.
Yeah, that's true. Okay, that could be true. Yeah, because actually the dark matter only let's see which ways to go. The dark matter only tends to be more squashed.
Yes, I have this. Just give me a second. I just have to remember where it's at.
Yeah, if you're making baryons, probably also self-interaction because now it's.
I mean, this would be nice. This would be a nice physics story to tell if it worked actually, but
Yeah.
I'm just like I'm not sure if it actually.
I don't
I'm
know.
not sure if it actually works.
Talk about this because I think that there if you.
I mean, it could
There you
be.
go. This is what you were asking, basically, right?
Yeah, what's the axis for? Yeah.
So this is the dark matter only simulation, so you can see that so B over A is the big axis, C over A. Sorry, A is the big axis everywhere. B is the intermediate axis, and C is the small axis. And so for the dark matter only simulation, it's sort of footballing like, I think, right?
Yeah.
And then, but for 1536, it's the small axis is not very close to 1, but for 15784, it's pretty close to circular.
Okay, so that's consistent with what other simulations have shown here too, because even self-interacting dark matter without baryons tends to give you halos that are more round and more Maxwell-Boltzmann-like.
Right.
So there may actually, I mean, the physics may be real physics, may be real, right? And not just. Yeah.
Well, I'll be around till Tuesday.
Yeah, I
so
was gonna say, yeah.
if anybody has any other questions about this stuff in general, feel free to stop by. I think I'm on the 5th floor of 516.
516,
Yeah, 516.
Better keep you up there.
Okay, so if no more questions, let's thank Chris again.